I want to talk about our latest product, the BergKristall contact image sensor, delivering much better data, much more information than has been possible in the past. First of all, I want to tell you about the history of the BergKristall. Then I'll give a short introduction on what we can do in the future with this product. I'll give an introduction to the FPGA framework that's essential for the overall function of the sensor, including LED multiplexing, which is a very powerful technique, especially for things like shape from shading, also known as photographic stereo. I'll talk shortly about the relation between trigger precision and color matching that you can achieve with different sensor topologies. Give an introduction to the basic sensor structure, the regions of interest that we support, shape from shading technique, and an outlook on hyperspectral imaging and true color imaging. Vision has introduced CIS technology for industrial applications back in 2001. The improvements we introduced over office scanners back in 2001 were larger working distance of 10 mm and more, line rates of up to 90 kHz, a rugged industrial housing and a 24-volt DC power supply, industry standard interfaces such as CameraLink or GIGI at that time, improved illumination like coaxial light, large width scanners with modular design up to 2 meters, 3 meters, 4 meters, and the shading correction done in hardware to release the software from doing shading correction. In the following years, we added staggered zero-gap sensors with geometry correction. What we do is that we stagger the sensor chips to create overlap, and with support of a FIFO, we can get a complete gapless line, while the conventional inline sensor has gaps between chips and larger gaps between substrates. We used LED multiplex to create multiple images from a single sensor, and we introduced switchable resolution so that the sensor can switch to any resolution from 1200 dpi down to maybe 50 dpi, or 20 micrometer pixels up to 0.5 millimeter pixels. During the last years, during the last decade, we got continuous customers' complaints because they want higher speed and higher resolution. So we started with the development of a sensor chip with an advanced 5-transistor pixel cell for best image quality. The 5T transistor cell gives us two advantages. One is lower noise and lower crosstalk, better black level, and the other advantage is that we can interleave illumination and imaging even better than in the past. The next goal was to get 1 megahertz line rate, 1000 kilohertz, to get a 12-bit grayscale resolution, and to have a 1200 dpi pixel field. I explain the applications later, plus an additional single 4800 dpi line. 1200 dpi is 21 micrometer, 4800 dpi is some 5.5 micrometer. And we requested on-chip digitization and a direct FPGA interface to keep the system simple and cost-effective. This sensor can only be reasonably used together with an FPGA backbone. The FPGA backbone supports things like advanced trigger control for applications requiring start-stop. If your conveyor belt regularly stops between P's, need to handle this. An integrated illumination controller that supports multispectral imaging and that supports shape from shading. 1D and 2D regions of interest, so that the huge amount of data that our sensor can deliver is limited to the regions of interest our customer needs right at the front end, and binning to the required resolution, so that our customer can choose any resolution from 4800 dpi down to 200, 175 dpi. Let me talk shortly about LED multiplex. Most color sensors that you know have one or another form of a color filter put onto the chip. This may be a primary color filter passing on 1/3 of the photons to the sensor, or a complementary color filter where you can pass on 2/3 of the incoming photons to the sensor. There are also CIS sensors in the market with the color filters. We do not use color filters. Instead, we use LED multiplex, meaning that if we build an RGB camera, we make a red flash, read the data in, make a green flash, read the data in, make a blue flash and read the data in, and then combine the 3 lines right into a single line output to the frame grabber. The LED multiplex has several advantages. The first, you are completely free with the color model. We can use 3 flashes, we can use 8 flashes for a hyperspectral camera, we can use 4 flashes for shape from shading as we do it, we can use a single flash and have a monochrome camera. The same chip and even the same device, if you use a subset of the existing illumination, lets you create several images, and the images are correlated to each other with pixel precision. Another advantage is that the multiplex may also be applied to illumination geometries instead of colors. Meaning, we can make a front light image with a red, green and blue combination, as well, and with the same sensor a backlight image with red, green and blue. This is used in Germany, for example, to recover documents that have been shredded into complete documents with two-sided inspection with a single sensor. The same thing can be done for multispectral imaging. The best thing is the operation is LED multiplex is table driven. The table is set by the user of the sensor. The correlation, in practical applications, you always have a line trigger which is driven by the belt or by the motor or whatever moving mechanism, or by the drum, whatever moving mechanism you have. If you use color filters and separate lines, typically would be 8 line spacing, then you need a FIFO for compensating. The object line inspection reaches the red line first. 8 lines later it reaches the green pixels, and then 8 lines later it reaches the blue pixels. On the electronic side, you need a FIFO, maybe in hardware, maybe in software, that compensates this delay and joins the matching lines. Now this requires, the ones among you who have already used TDI know that with multiple line setup, triggering is very, very critical. The trigger fluctuation that's permitted with such a setup is 6% only before you start matching one line, matching line 16 of red with line 17 of blue. So this requires very high trigger precision. A solution with a single flash, a single line that's multiple flashed, is much more resistant to trigger fluctuations without distorting the image. Okay, I want to give you a short view onto the sensor structure. On top you see the LED boards that come in segments. Below you see the sensor boards. The sensor boards are connected to FPGA boards, and FPGA boards provide video output paths. A central controller board, the bottom left, controls the trigger, triggers the sensor boards and drives the light sources. A power supply distributes the power evenly among boards. What you see here is that you can share data between boards. So we can shift video data from one FPGA board to the next and output them through a single output. This is helpful for customers who do not have the processing bandwidth and work only with regions of interest. Regions of interest, this is a typical application from security print. This is a banknote dummy. Everything else is, I think, forbidden in Germany. And if you look at the banknote, then there are actually only 4 or 5 regions of interest that you want to inspect for safety. And these regions comprise an area of maybe 3 to 5% of the total banknote area. So if you, like we do it, support 2-dimensional regions of interest, as I have shown it here, you can cut the amount of data inside the sensor to 3 to 5%, which means you save on cabling, you save on frame grabbers, you save on PCs, you save on processing power. So 1 and 2-dimensional regions reduce the workload for the machine vision system. Shape from shading or photometric stereo is another application for multiplexed LED. What you see here is a pharma package. On top you see 4 raw images created with shape from shading, meaning you light from the left, you light from the right, you light from top, you light from bottom. The 4 images are appear more or less identical to the eye. If you apply standard algorithms, then you get a gradient X image, a gradient Y image, a height profile, and an albedo profile which contains color information but no 3D information. The image on bottom shows the extracted height information converted into a 3D view. So you can really extract any tactile phenomenon like here for blind people. Banknotes must be recognized by blind people. A pharmaceutical package must be read by blind people. And these tactile features required for blind people can be brought out very clear using shape from shading. Okay, last foil is the BergKristall sensor, as you will explain later, has also been designed for hyperspectral imaging. If we combine, the BergKristall chip supports 48 active video rows. Combined with a dispersive element, it could be a prism, could be a grating, the sensor will deliver spectrally resolved lines. Due to the high speed, we can deliver 20,000 full spectra per second, meaning we can run 20,000 spectra per second. With 300 dpi resolution, this means we can do inspection at 100 meters per minute with full spectral resolution. To handle the bandwidth, we will include a converter that's customer programmable inside the sensor and deliver only the true colors, red, green and blue. So again, data reduction at the front end. Okay, Andrea will continue outlining the chip behind the design.
So I will show you how the chip is built inside. It's a nice opportunity for me for the first time to show what we do in silicon together what is done in application. Normally these worlds are disconnected. So this is the silicon that we have developed for T-Hour. It's a pixelated array, 1.5D sensor, it's called like that, with 52 times 876 pixels, plus 1 row at 20 micron, plus 1 row at 5 micron of dimension. And we allow full external addressing for the row, so we can control each row exposure, reset, conditions independently. We read out the value of the pixel in an interleaved way, so we can pretty much pipeline the conversion to get these 1 million rows per second readout that is needed for the application. We can change this resolution. We have an ADC on board, so we can change the resolution between 8 and 12 bits. And the technology we use is 180 nanometer and with 5 metal layers. Just to go into the details, the presentation is higher level. If you want more details, we can discuss. Also, we implemented a multiplexing from 8 to 1 channel exactly for the reason that was just mentioned, to do data reduction when possible. The sensor is about 20 millimeters by 5 millimeter. The sensitive area is almost as wide. And you see in a block diagram, you see the pixel array is on the top. Then we have a huge amount of ADCs. It's pretty much double than the number of columns of ADCs. Each ADC converts a portion of the image, pretty much a vertical portion of the image, and it sends the data to the digital part and at the end to the output drivers and the output multiplexers. How did we implement the dual resolution? This is a zoom in of the pixel array on one corner of it. We have a region where we implement the 2400 dpi resolution, so this is 20 micron pixels. And we have a region where we implement the 4800. They are interleaved, so they are supposed to get exactly the same alignment, exactly the same image quality, exactly the same lighting. The pixel we used is kind of standard. It's just slightly different from a 40. It's a 5T, where we allow also the reset of the floating of the photodiode itself, so that we are sure that we can keep a row in reset constantly, that doesn't get any bleeding to the neighboring rows. And we can implement a rolling shutter and global shutter as needed by the application. The ADC, it's a bit going to detail, is a single ramp ADC, so it's normally used for, let's say, non-extreme resolution, 8 to 10, 11 bits or so. You use ramp ADCs. First you convert the reset level, then you convert the signal level, so the exposed level, and you do the difference between the two, and it gives you a CDS, a digital CDS. Or you can do a CDS analog in advance, so you sample the value of the reset, you subtract the value of the signal, and you convert that directly. So all these modes are supported. The ADC is implemented in a 10 micron pitch, so we use 2 ADCs per column, and this ADC is able to, like I said, implement both digital and analog CDS, and we use a programmable ramp generator that is common for the whole array. There is a single ramp generator that runs through all the ADCs, and it needs to be quite precise to program the start and the end of the slope. I will go quickly, otherwise, oh well, it was okay. So this shows a bit the digital interface. We have counters that can be used also for doing differences. They are optimized for the functionality, and they can be used also as shift registers to bring the data out to the serializer, all optimized for the application. So our company specializes in custom image sensors. So if you have any needs, you can come to visit us. We can discuss your needs. We can figure out how to serve you best with either products we have or with customized versions of the products that we have done.
So much.
Thanks.
Thank you. Do we have questions? We still have 3 minutes for questions. It's okay. No questions from the audience, but I have a question on the slide where you showed where you're using the sensor. So I'm just curious to know what has been, in your experience, the most challenging implementation of the sensor, and why? Where you had a problem statement where you had to implement use the features of the sensor, and then you faced some challenges.
CIS technology or this specific sensor chip? Which one? This
one, the one that you presented with the accuracy of color correction, like accurate colors, representation of accurate colors. That one.
The biggest challenge to come is the hyperspectral version, because we have a spectrometer every 16 millimeters. So we have 96 spectrometers or 48 spectrometers, and all the spectrometers must be in tune. And this requires some smart engineering, like closed loop calibration, spectral calibration with laser lines, tricks like that. Yes, maybe a piezo tripod for adjusting during operation. It's very easy. It's very easy to build a single channel spectrometer. It's much more complicated to build 96 spectrometers in one housing.
Okay.